Okay, now we're going to solve the same problem in a more realistic setting, where instead of having an isolated system with just the gold and the water, we have a real calorimeter. And this here is an example of a calorimeter we use in our labs. But we're still making a hypothetical situation that we're saying that this is a ideal calorimeter in the sense that no heat escapes from this calorimeter. But when I drop, so I have into this 25 grams of water, and when I drop the hot gold into it, both the water and the calorimeter absorb the energy. So I have two cold objects. So once again, as in the prior, I can say that Q cold is equal to minus Q hot. The difference is that now in the cold object, I have the water, the Q of the water, plus the Q of the calorimeter, which is equal to minus Q of the hot. Now, the Q of the water is equal to the mass of the water times the specific, we're going to call the water the cold object. So we're going to say the mass of the cold times the specific heat capacity of the water, the cold water, times the delta T of the cold, plus the C of the calorimeter times the delta T of the cold. Now this gives us an idea, once again, to look at the difference between capacitance and specific heat capacitance. Specific heat capacitance is like an intensive property. It's a property of the water. And when I multiply it by the mass, I have the capacitance of 25 grams. If I'd had 50 grams, I would have had twice the capacitance of 25. Whereas here, I'm talking about an object, okay? And we had to measure this capacitance in a separate experiment. Now this is equal to the heat lost by the gold, which is equal to the minus the specific, the mass of the hot object, times the heat capacity of the hot object, times the delta T of the hot. So now I'm going to bring these these things under the same thing for the delta T. So I have the mass of the cold water times the specific heat capacity of the water, plus the calorimeter constant, times T delta Tc, which is equal to Tf minus Tc. And now I have this is equal to the mass of the hot times the specific heat capacitance of the hot, the gold, times Tf minus Th. And once again, the hot object cooled, the cold object warm. Now, in the absence of the calorimeter, we concluded that the final temperature, Tf, was equal to 30.17. Now that I have two objects absorbing it, it has an even greater capacitance, so we're going to expect the final temperature to be less than 30.17. So we're going to expect this to rise, but not rise as much as it did the last time, and this is still going to drop. In fact, it's going to drop more, because we have more cold material to absorb the heat. Now I solve for Tf, and I have everything on this side I'll put for the Tf. So I have the mass of the cold times the capacitance of the cold. I have a W here. Remember, this is cold water. Times plus the calorimeter constant. And we usually use a capital C for that. And then I have a minus MHCH here. So when I bring it over here, it becomes a positive MHCH. And this is all times Tf. Now over here, I have my minus MHCH-TH. So I have my MHCH-TH. And now I have my Tc as a minus CW, which is the cold. So this becomes a positive, because I bring it to the other side, MCCC-TC. And now I have my Tf is equal to MHCH-TH plus MCCC-TC, which is identical to what it was in the absence of the calorimeter. But now in the denominator, I have my MCCC and my MHCH, which I had before, but I also have my C calorimeter. So the denominator has gotten larger, so the final temperature is going to get smaller. MHCH, I add that, and I now substitute my numbers. So I've got, 2 grams of the hot object. It had a capacitance of 0.128 joules per gram degrees C. And the initial temperature was 100 degrees C. And I add to that the mass of the cold, which was 25 grams, because water has a density of 25 grams per mil, times its capacitance of specific heat capacity of 4.184 joules per gram degrees C, times the cold temperature, which was initially 30 degrees C. And now I divide that by the mass of the hot times its specific heat capacity of the hot, plus the C of the calorimeter, which is 36 joules per degree C, and plus the mass of the cold, 25 grams, times 4.184 joules per gram degrees C. Okay, and I now pull out my calculator, and I come up with a final temperature of 30.12 degrees C. Okay, and technically this would be 30.1 with 3 significant digits. And I now can see that before it was 30.17 or 30.2, so indeed it didn't rise as much as it did in the absence of the calorimeter, and that's because in a real calorimeter, the object actually does absorb some heat. We still haven't taken into account everything that we could, because this object is not thermally isolated from the environment, and energy is transferred, and eventually it would reach room temperature. Thank you.